So friends, I will start with a new extraction technique, and this technique is largely used at commercial level by industries to extract out the desirable components from the different types of matrices, and this technique is known as supercritical fluid extraction. We will discuss this technique starting with their brief historical overview, followed by its principle and mechanism, that how it enhances the extraction yield. Then I will discuss about the instrumentation aspect of the technique, what are the different components that are involved in the instrument or the equipment that is used for this technique. This will be followed by the factors that can affect the extraction efficiency of this process, and lastly we will discuss about the applications of this technique. So starting with the historical overview of this technique, it all started in 1822 when Baron Cagniard de la Tour, he defined or he described the critical values or critical point of a substance. Though he did not give the term critical point, but he described the properties of a substance at that particular point. In his experiment, what he did was he took a barrel of a gun, and that barrel was filled with a liquid, and a small metallic ball was dropped in that barrel. Then he sealed both the ends of that barrel and he started heating that barrel at a specified pressure value. And in between, he always tapped the barrel in order to hear the sound of that metallic ball. So he started noting the change in the sound of that metallic ball with respect to the change in the value of temperature and pressure. And he found that at a particular value of temperature and pressure, the sound of the ball completely stops. And that was the point which we now know by the name of critical point. For many years, until 1869, this point of temperature and pressure value was largely known by the name Cagniard de la Tour point. Until 1869, when Dr. Thomas Andrews, he defined this point as critical point when he was doing experiment on carbon dioxide. So he exposed carbon dioxide to specific temperature and pressure values where he found that carbon dioxide coexist in a liquid and gaseous state or gaseous phase. And then he gave, because this was a critical observation with respect to the behavior of carbon dioxide, therefore he gave this particular point the name critical point, and this is how this term was generated. Now, following the experiment of Dr. Andrews in 1879, Henne and Hogarth, they again performed an experiment wherein they used a narrow glass tube, and you can see the image of glass tube in the picture, which is the A image, and B represents the whole setup of that experiment. So what they did was they take certain different inorganic salts and they take ethanol as a solvent. They basically observe the solubility pattern of those inorganic solute molecules into the ethanol by changing temperature and pressure conditions. They found that at a particular temperature and pressure value, those inorganic solutes get dissolved in ethanol, and as they decrease the pressure, the inorganic salts, they get nucleated and they precipitate as snowflakes out of ethanol. So again, this was a very critical observation that was reported by Henne and Hogarth, and perhaps this was the basis of the utilization of supercritical fluid for solubilizing and for extraction. Following their experimental observation, almost 20 years after their experiment, Villard in 1896, again he reviewed the solubility profile or phenomena of different supercritical fluids using inorganic salts, and the supercritical fluids which he used was methane, ethylene, carbon dioxide and nitrous oxide. Again in 1906, Buchner made a significant contribution to the data by publishing the experimental data of different solute mixture and their solubility profiles under supercritical conditions. So this was a significant addition to the database which was given by Buchner. And again, this database again motivated various other scientists to work in this direction. And in 1916, Prince he gave the solubility profile of naphthalene in under supercritical conditions in both ethane and carbon dioxide. But unfortunately, since the mechanism was not fully elucidated, there was the interest in the supercritical fluids was decreased substantially until 1948, when Professor Scheffer and his group they published extensively on the solubility profiles of ethylene and naphthalene under supercritical conditions. They also tried to elucidate the mechanism how the solubility profile changes with the change in temperature and pressure conditions, and because of their experiment there was a revival in the interest in these supercritical fluids. Following their experiments in 1954, Francis exhibited the solvent properties of carbon dioxide with numerous compounds, both non-polar as well as polar compounds. So what he did was he exposed carbon dioxide to supercritical conditions and studied the solubilizing power of carbon dioxide on various compounds. Then in 1984, Schmidt and Reed, they again utilized the solubilizing data that was given by Buchner and Prince on naphthalene, and they studied the solubilizing of naphthalene in different solvents under supercritical conditions. It was late 20th century, perhaps this was the first report of utilization of supercritical fluids for extracting out secondary metabolites from the plants, and wherein caffeine was extracted from tea waste and coffee beans. And once the extraction of secondary metabolite was successful, this gave an impetus for utilization of supercritical fluid at commercial level. Though very less information was available at that time regarding the commercial application of this technique, but at laboratory level, lot of advancements and lot of interest was generated when the first report on utilization of supercritical fluid for extracting out secondary metabolites came into picture. Then in early 21st century, a second report came wherein cannabis oil was extracted from the cannabis plant. Now, it was not only the developments were made in the field of utilization of supercritical fluid technology in terms of extraction only, but this technique was coupled with various other analytical techniques over the period of time. Like the supercritical fluid extraction technique was coupled with mass spectrophotometry in 1986 by Kalinowski. It was again coupled with gas chromatographic equipment in 1918 by Hawthorne. Then with FTIR by Kirshner and Tyler in 1992, and eventually in 1993, Cotton and his group, they coupled supercritical fluid extraction unit with supercritical fluid chromatography. Now, the major benefits that arise by coupling or hyphenation of supercritical fluid extraction technique was that there was a significant reduction in the handling of the samples. We know that because we have to analyze the extract that is obtained after using a particular extraction technique, and it has been observed that majority of the errors that are incorporated into analytical process are due to the manhandling or improper handling of the sample. So by coupling the two techniques, one is extraction and other is analytical equipment, the sample handling errors were reduced, and it's not only the errors but the loss of the sample was also reduced. Contamination of the samples was also reduced, and eventually the overall analysis time was reduced when the supercritical fluid extraction technique was coupled with different analytical equipments. Now we move on to the mechanism of this technique. We were talking that in the past various experiments were done wherein different solvents were exposed to supercritical conditions and they get converted into supercritical fluids. But the question is, what are supercritical fluids. So whenever a substance is exposed to temperature and pressure conditions which are more than the critical values of pressure and temperature, then that substance enter into a supercritical phase, and once it enter into a supercritical phase, we call it as a supercritical fluid. So if in simple words I say that a substance in a supercritical phase has properties of both gases and of liquids. Now if we talk about the extraction process, basics of extraction process, we know that solvent first diffuses into the matrix. After diffusing in, it solubilizes the solute molecule and then it diffuses out. So the major rate limiting step in the extraction, if we talk about, is the diffusivity of the solvent into the matrix. Then comes the solubility. So once the solvent get diffusivity of a gas, and we know that gases have high diffusion coefficient, they can easily diffuse into a matrix. So if a solvent gets high diffusion or high diffusivity like gases and retain its solubility like liquids, the extraction efficiency can be increased many folds. Now we are overcoming both the rate limiting step by exposing a substance to supercritical conditions. Now this can also be understood by this graph, wherein I have taken an example of carbon dioxide. So you can see that at a temperature of almost around 220 or 225 Kelvin, which is almost around minus 50 or 53 degrees Celsius, and a pressure of around 6 to 7 bars, a point exists at these values where carbon dioxide exists in three phases, that is solid, liquid and gas. And as we increase the temperature beyond that triple point and pressure beyond the triple point, the solid phase gets removed, and now the carbon dioxide, which is actually a gas, exists in both liquid and gaseous form up to the temperature and pressure value at critical point. Now when we further increase the temperature values above the critical point and above the critical temperature, there is no separation of the phases, because between the triple point and critical point, carbon dioxide gets biphasic and exists in liquid as well as in gas form. But at the temperature and pressure conditions above the critical point, then we get a homogeneous phase where one cannot differentiate between the liquid and gaseous phase of the carbon dioxide. Now I will again go back to the triple point. If we reduce the temperature and pressure conditions below the triple point, then the carbon dioxide mainly occur as solid and gas. And this is the condition which when carbon dioxide occurs in the form of dry ice. So we are further decreasing the temperature below a triple point, which causes the solidification of majority of the carbon dioxide, and because it's very difficult to maintain that temperature below triple point under normal circumstances, therefore dry ice occur in both solid as well as in the gaseous phase. So this was an example how the effect of pressure and temperature changes the properties of a substance. And if we talk about properties, then obviously major one is the density. So we can clearly say that the possibility of a solvent to be used as supercritical fluid will largely depends upon its density, and density will also govern the solubilizing power or the solubility of the solute into that particular solvent. And this correlation of the solubility of solute with respect to the density of the solvent was very well explained by Karstell in 1982 by the equation which you can see on your screens. Here S is the solubility of the solute, rho is the density of the solvent, T is the absolute temperature, and A, B and C are the correlation parameters that obviously have to be adjusted according to the experimental conditions or the experimental solubility. So we can clearly see through this correlation that solubility of a solute is directly proportional to the density of the solvent. But there was a limitation of this equation, that it gives you a relation between the solubility of a solute and the density, but this relation does not guarantee you the high solubility of the solute into a particular solvent. Before we move on to the limitation aspect, that how we can overcome this limitation, the solubility and density, the correlation between two can be easily seen in this graph at particular temperature values. The solid line is at 330 kelvins of temperature, and you can see as we increase the density, the solubility of a particular solute in that solvent increases considerably, and same happens at lower temperature values. Now coming back to the limitation of the Castell equation, as I told you that it does not guarantee the high solubility of that particular solute, and we can always calculate the solubility of a solid by fugacity criteria. Now fugacity criteria is nothing but the variation of the chemical potential of a substance under critical condition with respect to the chemical potential of that substance under standard conditions, and this is represented by the equation Y2 is equal to E, which is the enhancement factor, thereby giving a ratio of P2S and P. PS2 is the sublimation pressure of the solute and P is the absolute pressure. Enhancement factor is the enhanced solubility of a substance of under critical condition with respect to its solubility under standard conditions. Now we can always calculate this enhancement factor by using this equation, and by seeing this equation we can easily correlate that enhancement factor is inversely proportional to the fugacity of a solvent, which is represented by phi square. Now fugacity is nothing but the change in the chemical potential. So it's not only that we have to expose the substance to supercritical conditions, but we have to maintain the change in the chemical potential to a minimal value. And once we maintain that change in chemical potential to minimal value, the enhancement factor increases, that is the solubilizing of the solute increases. So it's not only to expose the solvent just to supercritical conditions, we also have to maintain its change in the chemical potential of the solvent. Now another important factor in case of extraction is the selectivity. So till now we have discussed about the solubility, now we will discuss about the selectivity of that particular solvent. And it is defined as the ratio of the solubility of a substance of interest with respect to the reference substance. And with tremendous literature that is available on the studies for the selectivity of the solvent, it has been found that selectivity should always be as far as possible from the value 1, because if the selectivity is closer to 1, then it indicates that during the extraction process various other compounds will also get extracted along with the desired compound. So in order to extract out the compound of interest, the selectivity should be very high in comparison to with respect to that particular solvent, and therefore its value should be away from 1. So as soon as the selectivity value reaches to 1, the effect of selectivity decreases, and therefore other compounds also get extracted. Now in this table you can see the properties of a solvent when it is present in a gaseous form, when it is present in a liquid form, or when it is present in a supercritical form. And these properties can be defined in terms of density, dynamic viscosity, kinematic viscosity, diffusion coefficient, and thermal conductivity. And all these factors affect the extraction efficiency in one manner or other. So we can clearly see that the density of supercritical fluid lies somewhat between gas and liquid phase. Dynamic viscosity, again, it is much lower than the liquid when the solvent is present in the liquid phase, and it is slightly higher when the solvent is present in the gaseous phase. Again, kinematic viscosity lies between a gas and the liquid phase, though the kinematic viscosity is much higher for gases, whereas supercritical fluids have lower kinematic viscosity in comparison to the liquid. Diffusion coefficient, we discussed that supercritical fluids have diffusivity same as that of gases, and it's much higher than the liquid. So we can clearly see in the table for gases diffusion coefficient is in the range of 10 to 40, for supercritical fluids it is 0.07, and for liquid it is 0.002 to 0.002. Same is in case of thermal conductivity. Supercritical fluids have thermal conductivity much higher in comparison to those of gases and liquid. Now this table comprises of various solvents that can be used as supercritical fluids, and I have arranged these solvents in increasing order of their critical values of their temperature. If we critically go through this table, we can clearly see that carbon dioxide is the only solvent that can be used at ambient conditions. For other solvents like hexane, ammonia, methanol, water, we have to heat up the solvent to much higher temperatures beyond the ambient conditions. And therefore, since carbon dioxide can be used as a supercritical fluid at ambient conditions, this is always considered as solvent of choice in case of supercritical fluid extraction. And it's not only that it can be used at ambient conditions, therefore it is solvent of choice. There are other factors also which we are going to discuss ahead. Now, on the basis of the critical values of their temperature, solvents can be classified into low critical temperature solvents and high critical temperature solvents. And the examples of low critical temperature solvents are carbon dioxide, ethane and propane, and as we saw in the table, high critical temperature solvents are methanol, water and higher alkanes. Now, since there is large difference in the critical temperature values of these solvents, there is a strong difference between the solubilizing power of these solvents and also the selectivity of these solvents. The solvents which are low critical temperature solvents, they have better selectivity but a limited solubility. But in case of higher critical temperature solvents, they have low selectivity and higher solubility. Now we can also differentiate these solvents, as you can see in this table. The low critical temperature solvents have high solubility for low molecular weight compounds, or we can say non-polar compounds, whereas high critical temperature solvents have high preference for high molecular weight compounds or polar compounds. But it has also been seen that these high critical temperature solvents have wide solubilizing power. They can solubilize non-polar to medium polar and to polar constituents. Therefore, solubilizing is high, selectivity is low. And since low critical temperature solvents, they are only used for non-polar compounds, therefore they have less solubility but high selectivity. Now, as we discussed that low temperature critical solvents can be used at ambient conditions, whereas high critical temperature solvents, for them we have to use high temperature and pressure conditions. And since we have to use high temperature and pressure conditions, they may cause the thermal degradation of certain constituents, whereas such problem is not faced when we are using low critical temperature solvents. And another advantage of low critical temperature solvents is they can be easily separated from the extract. By slight variation in the temperature and pressure conditions, we can easily separate out these low critical temperature solvents in comparison to the high critical temperature solvents. Now we come back to why carbon dioxide is preferred. Now, carbon dioxide is largely considered as a non-polar or a hydrophobic solvent, and therefore it has high selectivity for the non-polar constituents. Further, this, if you can see the structure, the carbon molecule, the carbon atom is surrounded by two oxygen atoms which are electronegative, and their electronegativity is nullified, and therefore this compound is considered to be highly non-polar. And not only non-polar, it is highly non-inflammable, which is another reason why carbon dioxide is a preferred solvent. Stoll and Quirin, they studied this molecule with respect to its selectivity and solubilizing, and they found that the hydrocarbons having up to 10 carbon atoms and lipophilic compounds with low molecular weight and polarity can be easily extracted by carbon dioxide. And when we add polar groups to the different compounds like hydroxyl or carboxyl groups, then the solubility of such compounds decreases in carbon dioxide and they make their extraction difficult. Highly polar compounds like sugars and amino acids cannot be extracted by carbon dioxide alone. Yes, you can even extract highly polar compounds with carbon dioxide, but that can be done by adding certain other solvents, high polar solvents like methanol or ethanol up to a specified concentration in order to change the solubilizing property of the carbon dioxide, and by adding such solvents we can also extract the polar components. And once we add the solvents, highly polar solvents at a lower percentage like methanol and ethanol we discussed, when they are used with carbon dioxide we call them as co-solvents or entrainers. Now this is again the graph which shows the critical values of carbon dioxide, and as I told you that below triple point it occur as a dry ice, and above the critical point it occur as a homogeneous phase wherein we cannot differentiate between the liquid and gaseous phase of carbon dioxide, and under those conditions we call it as supercritical fluid, and that is why it is largely used as a solvent in supercritical fluid extraction. Now here are various advantages of carbon dioxide which is used as a supercritical fluid. We discussed that it is non-toxic, non-corrosive, non-inflammable. It can be reused because it can be easily separated from the extract, therefore it can be reused. It's readily available in large quantities and high purity. We can get high purity carbon dioxide if we want to extract out specific components, and because of all these factors, regulatory agencies also accept carbon dioxide as a solvent to extract out secondary metabolites or the components from the food items. It has, because it is gaseous in nature, it has high diffusivity, and because of its properties under supercritical conditions, it provides better solubilizing power, and as we discussed that it can be easily separated from the extract. The resultant product which we get is almost free from the solvent residues. Apart from its advantages, there are various limitations of carbon dioxide because it is non-polar as we discussed and lipophilic, so only non-polar or lipophilic compounds can be extracted. But yes, you can also extract highly polar compounds by using co-solvents and entrainers, and the examples of co-solvents and entrainers we discussed are ethanol, methanol at a specified concentration we can use. So friends, in my next lecture we will further discuss about this wonderful extraction technique, and we'll discuss about the instrumentation, the factors that can affect the extraction efficiency of this technique, and in the end we'll discuss about the application of supercritical fluid extraction. Thank you.